with a bit. Okay, so good evening, class. Last week we discussed gas laws, where we talked about the different gas laws, Boyle's law, Charles' law. We also talked about the ideal gas equation, the pressure law, and we also talked about Avogadro's law. And there we said that Avogadro's law says that for equal number of for gas with same volume and pressure, they all have equal number of particles. So, and we established for these particles is a constant that is given as 6.02 times 10 raised to power 23. So today we're in this number and see how it relates to what we call mole and the molar volume. So straight up, let's talk about the mole. What is a mole? Well, mole in chemistry is not a dent on the face or an animal that bores hole in the soil, but is actually refers to the Avogadro's number of the particles of any substance. So a mole refers to the Avogadro's number of the particles of any substance. What do we mean? Based on what we said, every substance has a particular number of particles as long as it is one or a mass of that substance, it is 6.02 times 10 raised to the power 23. By comparison, what we are saying is same thing as 12 eggs is the same as 1 dozen of eggs. 30 eggs is the same thing as 1 crate of eggs. Half dozen is same thing as 6. A score is same thing as 20. So once we have a particular number, say, let's now bring it to a practical example, 1 mole of water. 1 mole of water is the same thing as 6.02 times molecules, or we could say particles, depending on what we are saying. In this case, water. This will also stand for every other compound. Say sodium chloride. 1 mole of sodium chloride is same thing as 6.02 times 10 raised to the power 23 molecules of sodium chloride. 1 mole of sodium triisocarbonate is same thing as 6.02 times 10 raised to the power 23. You can think of any compound. All compounds, as long as 1 mole of that compound contains 6.02 times 10 raised to the power 23. Now, this 1 mole is the same thing as the atomic mass of that compound being 6.02 times 10 raised to the power 23. What do we mean by this? We do know that the atomic mass for, say, sodium is 23. Now, that means that 23 represents one atom of sodium. So that means 1 mole of sodium, the same thing as 23 grams of sodium, contains 6.02 times 10 raised to the power 23 molecules of sodium. Please, let's take note of this, that the atomic mass of each element is the same thing as 6.02 times 10 raised to the power 23, or 1 mole of that element. Please, let's take note of this. It's very, very important. So let's take examples. Let's take some examples. The first example here is, how many molecules are there in 4.0 moles of glucose? Now here we have the solution. Remember, as we have said, 1 mole of every compound is equal to 6.02 times 10 raised to the power 23 molecules. So I've written it there as 1 mole of glucose contains 6.02 times 10 raised to power 23 molecules of glucose. Now, what we are looking for is 4 moles of glucose. So we say 4 moles of glucose will contain, we are looking for that, right? So taking that to the next line, 1 equals 6.02 times 10 raised to power 23, and then 4 equals x. Basic mathematics, cross multiply, we'll have 1 times x equals 4 times 6.02 times 10 raised to power 23. If we do that on a calculator, you will get 2.41 times 10 raised to power 24 molecules of glucose. This means that for every 4 moles of glucose, we have 2.41 times 10 raised to power 24 molecules of glucose. Now, why is it that we have it as 24 here? If we use our calculator to try out this equation, that is 4 times 6.02, what you get is 24.1. Now, by the time you round it or you bring the decimal point forward, then you bring the decimal point forward, it will be at 2.41. And that will mean that your power would increase with 1. So that's why we have it as 2.41 times 10 raised to power 24. Please, do we have any question based on this? I'd like to entertain questions, please. Any question? Okay, if there is no question, can we try out the second one, please? How many molecules are there in 1.46 moles of aluminum fluoride? Please, I would like us to try it and bring the answer so we would know if we really understand this part before we move on, please. I want this class to be interactive. Or can anyone just try and explain the process with which we would try to solve this question? Is anyone willing to try? Okay, I think if no one's willing to try, I would start calling names and asking questions. Okay, Fasonu Oluwatobi, please. We have aluminum fluoride. How many moles of aluminum fluoride do we have? Or how many molecules of aluminum fluoride do we have in 1 mole of it? Sorry? Oh, it's really cracking.
Maybe
Can you try again, please? Ah, it's still breaking. Sorry about that. Let me try someone else. I couldn't get that at all. Let me try someone else. Sorry about that. Okay, let's try Lizzie. Lizzie, please, can you help us out with it? How many molecules do we have? How many molecules of aluminum fluoride do we have in 1 mole of it?
Sorry, Lizzie might not be able to answer the question because she didn't connect to her audio for her to be able to hear us.
Oh, okay.
Guys, please just try to respond to the tutor. Time is going. Just try to respond.
Okay, so let's just move on. So the solution to that would be here. So we have 1 mole of aluminum fluoride contains 6.02 times 10 raised to 23 molecules. Now, if we are to now bring in what we are looking for, which is 1.46 mole. So 1.46 mole will contain X. By the time we equate that, it will be 1 equals 6.02 times 10 raised to 23, and then 1.46 equals X. Basic mathematics, cross multiply. You have 1 times X equals 1.46 times 10, 1.46 times 6.02 times 10 raised to 23. We do know that X times 1 will still give you X. So 1.46 times 6.02 times 10 raised to 23 will give you 8.7 times 10 raised to 23 molecules. So it's that simple. You always have at the back of your mind that 1 mole of the substance, no matter what the substance is, will be equal to 6.02. And then bring in the value you are looking for. In this case, 1.46. It will contain X, what you will get. Now, another question under this is now bringing in mass, the atomic mass we spoke about earlier on. Here we have how many atoms are in 4.0 grams of carbon. We are giving the atomic mass of carbon to be C equals 12. Now, just as I said earlier, 1 mole of a substance is the same thing as its atomic mass. And it's still 6.02 times 10 raised 23. 6.02 times 10 raised to 23. Now, in this question, specifically asked how many atoms are in 0 grams. So that means they're not asking us for the number of moles. It's on the mass, which is 12 grams, and the Avogadro's constant. 12 grams or 6.02 times 10 raised to 23. Now, 4 grams will contain what? Equating it 10 raised to 23, and then 4 equals X. So 4 times 6.02 times 12, add both sides with 12. So that's why we have, and then equals 4.4 times 6.02. Then the next line we have X equals 24.8. That is after multiplying 4 times 6.02. Then dividing with 12, or dividing by 12, sorry, we have 2.01 times 10 raised to 23 atoms of carbon, please. Atoms of carbon. I hope we understood how we're able to bring in the mass here. Unlike the other questions we solved, where it asked about the mass, so where it's even giving the atomic mass. But in this question, we have been given the atomic mass or relative atomic mass of carbon being 12. So that's why we're able to equate it, and we have the answer to be 2.01 times 10 plus 23 atoms carbon. Now, in the case whereby you have a larger compound, say for example, so you have a compound that has different elements, how do we solve for this? To solve there with mass, or as we said, relative atomic mass. Now, for you to be able to calculate the molar mass or relative atomic mass, what you do is you have the formula molar mass equals atomic mass times number of atoms. So here we have the example for sodium chloride. So calculate the atomic mass of sodium chloride. We have, sorry, it should be molar mass. Sorry about that. It should be molar mass. Calculate the molar mass of sodium chloride. So we have the atomic mass being 23, and then that's for sodium, and then for chlorine being 35.5. So 23 times 1, because we have only one atom of sodium here. If the number was different, say 2 or 3, you have a small number. If it is 2, you have 2 written at the base or as a subscript of sodium. But since there's nothing written there, we do know that it is only one atom of sodium that is in this compound. So we represent that with 1. So we have 23 times 1. And then for chlorine, the atomic mass being 35.5 times 1, because we have only one atom of chlorine here. It was the relative atomic mass we were to calculate, there will be no units. But when you are calculating for molar mass, the unit is always in grams per mole. Please, let's try to take note of this, because in subsequent topics, we'll be needing the solution for molar mass. Now, this same formula goes for compounds like your sodium trioxocarbonate, hydrochloric acid, sulfuric acid, that is H2SO4. For the case of, say, sodium trioxocarbonate, which is Na2CO3, what we'll have there is, since we have 2 atoms of sodium, and then we have okay, what is that? We have 2 atoms of sodium and 1 atom of carbon with 3 atoms of oxygen. There you have 23 times 1 for sodium. Then for carbon, 23 times 2 for sodium. For carbon will be 12 times 1. Since we have only 1 atom of carbon, carbon is 12. For oxygen, you have 16 times 3. So by the time we equate that, we have about 100 grams per mole. So we can still try some other examples on our own. And when we check our textbook, we'll see how this comes up or how we can solve this. Now that's that for molar mass and relative atomic mass. Now let's talk about the molar volume of gases. From Avogadro's law, we are able to detect that 1 mole of any gas at STP, as we mentioned in subsequent class or previous classes, is standard temperature and pressure. So the 1 mole of any gas as its standard temperature and pressure has a volume of 22.4 dm cube. No matter the gas, oxygen, nitrogen, carbon 4 oxide, as long as it is 1 mole of it, it will have a volume of 22.4. So this number is also a constant, just as you have your Avogadro's constant. Now I have an example there. 1 mole of fluorine gas and every other gas has a volume of 22.4. No matter what the gas, no matter how big the gas is, it will always have a volume of 22.4 dm cube, as long as it is 1 mole of that gas. So here we have a question that brings in the molar volume of gases. Question is 500 dm cube of carbon 4 oxide molecules absorbed by the leaves of an Iroko tree every day. How many moles and how many grams of carbon 4 oxide does this represent? How many moles and how many grams does this represent? By giving the molar volume at STP, which is 22.4. Now, how do we solve this? To find the molar, so to find the number of moles, first of all, we have 22.4 dm cube, which is a constant of CO2 is equal to 1 mole of CO2. That is, we have already said it earlier that 1 mole of every gas contains 22.4 dm cube. So 22.4 dm cube of CO2 is same thing as 1 mole of CO2. And remember, the question says 400 dm cube of this CO2 that is absorbed on a daily basis. So 500 dm cube equals to X, because we are looking for how. So when we cross multiply, we have X times 22.4 equals 1 times 500. So equating that, we have X equals 500 divided by 22.4. How do we have this? X times 22.4 will be 22.4x. And on the other side, we have 1 times 500, which is 500. So for us to leave X alone, we have X or 22.4x divided by 22.4, and that will cancel out that side. Then we'll be left with 500 divided by 22.4. So our answer would be 223.2 moles of CO2 at 500 dm cube. That's the meaning. So this means that since 1 mole of CO2, that means 223.2 moles of CO2 will contain 500 dm cube. I hope we're able to take note of the difference between calculating the number of moles and calculating the molar volume, or the volume of the gases. Now, the other part of the question was how many grams. We've calculated for how many moles already represent. So for us to calculate this, we'll calculate the molar mass first. So see here, the molar mass of CO2 equals 12 times 1, because the atomic mass of carbon is 12, and we only have 1 atom of carbon here, plus 16, which is the atomic mass of oxygen. Where is it? Times 2. So we have 12 plus 32, which will give us 44 grams per mole. So 1 mole equals 44.4 grams. Remember, we also said the molar mass too of each compound also represents 1 mole of that compound. So 1 mole equals 44 grams. Now, since from the previous question, we've gotten the number of moles, which is 223.2 grams that are produced in 500 dm cube. We now bring that into the equation. And bringing it into the equation, what we now have is 223.23 of CO2 equals X. So we have X will be equals to 223.2 times 44. When you cross multiply, and now give us 9,820 plus 0.8 grams of CO2. Please, is there any question so far? Is this understood? Well, I hope it is. So we move to the next part, which is vapor density. Now, what is vapor density? The vapor density of a gas is the number of times a given volume of gas is as okay. Hirat, you have a question. Please ask.
Not that I have a question. I'm just asking if I can see the question of what you just said. earlier because I'm just joining the class now. I'm sorry, please.
Oh, maybe I'll be able to do a quick recap when I'm done with this. I'll just do a quick recap. But just follow through from here, please. So, vapor density. So, vapor density of the gas is number of times a given volume of gas is as heavy as the same volume of hydrogen. So, for vapor density, we are comparing the volume of every gas to that of hydrogen, as long as it's at a particular temperature and pressure that is similar. No matter what the gas is, we are comparing it with hydrogen. Now, it is expressed mathematically as Vd, which is vapor density, equals the mass of a given volume of gas divided by the mass of an equal volume of, sorry, that should be hydrogen, please. That should be hydrogen divided by the mass of equal volume of hydrogen, not oxygen, please. Now, after carrying out or balancing each side and checking it out mathematically, the general formula that was now derived is vapor density equals 1/2 times the relative molecular mass of the gas, or vapor density equals half the relative molecular mass of the gas. No matter what the gas is, what they're telling you is, as long as you know the relative molecular mass or the molar mass of that gas, just divide it by 2. So let's say, for example, we are talking about oxygen gas. Now, the atomic mass of oxygen is 16. The atomic mass of oxygen is 16, and oxygen is diatomic, meaning it exists as 2 atoms. That's why we always see oxygen as O2. So if we are to find the relative atomic mass or the molar mass of oxygen, that will be 16 times 2. Now, 16 times 2 will give you 32. By the time you now divide that 32 by 2, that will give you 16. So that means the vapor density of oxygen gas is 16. Another example, say nitrogen. Nitrogen is monatomic, stands on its own as N. So if we have nitrogen gas and we are told to find the vapor density, the atomic mass of nitrogen is 14. So since it is monatomic, that is, you just do 14 times 1, which will still give you 14. So the vapor density would be half of that 14. That will give you 7. That means the vapor density of nitrogen is 7. So let's look at this example here now. So determine the vapor density of sulfur 4 oxide. The chemical formula for sulfur 4 oxide is SO2. So how do we go about it? Look at the solution here. We have molar mass of SO2, which is the atomic mass of sulfur times the number of atoms of sulfur plus the atomic mass of oxygen times number of atoms of oxygen. And mathematically, that is 32 times 1. We notice the subscript beside S there, there's nothing there, so we know that is 1. It's an invisible 1. So that will have 32 times 1. And then plus oxygen, the atomic mass is 16, and it has a subscript 2 there. So that means we have 2 atoms of oxygen there. So we have 16 times 2. So we have that as 32 plus 32, obviously, because 16 times 2 is 32. So that will give us 64 grams per mole. That is the molar mass for SO2. Now, finding the vapor density, remember, we say just divide by 2. So we have Vd equals half times relative molecular mass. That is half times 64, which gives us 32. So that means the vapor density for sulfur 4 oxide will be 32. So now we have another question here. If we understand this one, find the vapor density of water molecule having the relative molecular mass of 18. Who can give us the answer? A relative molecular mass, which is same thing as the molar mass of water, is 18. What is its vapor density?
9.
Beautiful. Thank you very much. Thank you very much. That is very correct. 9 is the answer. So vapor density is 9. So that means we understand this one very well. So just, I think we still have a few minutes. So I'll just do a quick recap on what we've taken so far. So we started with mole. We said mole refers to the Avogadro's number of particles of any substance. And last week we said that number is 6.02 times 10 raised to the power 23. And we said this is the same thing as saying 12 dozen is equal to, 12 equals to 1 dozen, 6 equals to half dozen, and a crate equals to 30 pieces and the rest. So for gases, what we have is 1 mole of any gas, no matter what the gas is 6.02 times 10 raised to the power 23, or molecules or particles, as the case may be. And then we solved some examples. Here we have 4.0 moles of glucose. So we said, okay, if 1 mole of glucose equals or contains 6.0 times 10 raised to the power 23, so 4 will contain what? By the time you use cross multiplication, you have 1 equals 6.02 times 10 raised to the power 23, and 4 equals x. When you cross multiply, you have 4 times 6.02 times 10 raised to the power 23. So you only multiply the 4 with the 6.02. That gave us, if you check on your calculator, you have 24.1. But by the time you bring the decimal point forward to make it two decimal place, you have 2.41 times 10 raised to the power 24 because you've moved the decimal point forward. So this goes for every other compound. As long as you are looking for the number of particles or the number of molecules, and with some different examples on that. Then we now came to, okay, let us say what you are asking for is number of atoms, and you are giving the atomic number. How do you solve it? In that case, you don't just compare the mole, but you also compare the atomic mass of that compound or the elements involved. Say, for example, this one of carbon here. So we have, instead of just using 1 mole of carbon, we now bring in the atomic mass, which is 12 grams of carbon, because the atomic mass of carbon is 12. So we have 12 grams equals 6.02, and equating that with 4 grams, which is what we are looking for, we have our final answer to be 2.01 times 10 raised to the power 23. Please, let's take note of the difference there. And then now we came to molar volume of gases. Just as we have Avogadro's constant, we have the molar volume of gases to be 22.4 dm cubed. It's standard for all gases. That is, when you have 1 mole of a gas, its standard volume at standard temperature and pressure will be 22.4 dm cubed. But you know that if it is 2 moles, that means that number will increase. It will double, meaning you multiply that 22.4 times 2. If it is 3 moles, you multiply times 3. So that is why we have this example here, that now we have 500 dm cubed. When you have 500 dm cubed, how many will it be? So equating that, we have 22.4 dm cubed equals 1 mole, 500 equals x, plus multiply, we have 223.2 moles of CO2. And then we had another question there that asked us for what is the mass. So then vapor density. So these are the main things we are covering for today. So this is the assignment for you guys. Please, I would love it if everybody submits the assignment this time around. Please, I really appreciate it to show how much you understand the class. So first question is, how many atoms are contained in 2 grams of hydrogen gas? Notice there that we've given the atomic mass of hydrogen to be 1. And the second question is, how many molecules of oxygen gas are contained in 0.2 moles of oxygen gas? O equals 16. Please, let's try our best to solve this and send our answers. The reason is this particular topic forms a basis for, or this particular subtopic forms a basis for so many other topics we'll meet in our upcoming classes. So I don't know if there's any question. Can I entertain any question now, please?
I'm sorry, sir. What I asked about, you don't answer. I said I need the question of what you solved. I just don't get it.
Sorry, I didn't get that. Can you repeat it?
When I entered the class, you are solving something. So I need the question of what you are solving.
I just took it back. I took it back to the beginning. So I think I explained the whole thing from the beginning already. So yeah, that was a recap I quickly did. Yes. So, and these questions are based on the beginning parts, Mole and Avogadro's number. So if you're able to go through it, you'll be able to understand how to solve it. In fact, it's just simple. Just compare the masses with the Avogadro's constant and you get the answer. So that's it. Please, so I'll be expecting our answers from tomorrow, if possible, even this night. You can, if you're able to solve it, you just send it up so we can compare it. So is there any other question? Okay.